Hello everyone and welcome back to Total Organic Chemistry. This video we're going to be taking an introductory look at cycloalkanes, which are very similar to straight chain or branched alkanes, but as their name implies, they are cyclic. So cycloalkanes are any alkane with some sort of ring structure. So cyclobutane, and these are named very similarly to the straight chain alkane, so 4 carbons is butane. We have cyclopentane, and cyclohexane. So these 4, 5, and 6 membered rings are some of the most common. And they form a lot of the foundations, or kind of the scaffolding, for a lot of natural products. Steroids, other natural products or things you might find in living organisms will be formed out of a lot of cycloalkanes. So before we get into discussing the compounds themselves, I want to take a look at stereochemistry. So a stereoisomer, we've talked about some other types of isomers before, but a stereoisomer is when you have two different compounds that have the exact same connectivity. So that means all of their atoms are connected at the same points throughout the molecule, but they differ in terms of where those atoms are arranged in three-dimensional space. So a different 3D arrangement. So, for example, if we take cyclopropane, so that's our 3-membered ring, and if we add one methyl substituent here, and I'm going to use the wedged bond to show that that's coming out of the page towards us, and then if I also draw cyclopropane with the dashed bond, remember the dashed bond is going into the page away from us, are these the same compound? Well, it turns out they are, because what we can do is imagine flipping this first molecule over, say, sort of a mirror plane. And then we get maybe this. So just mirroring it. And then all we have to do is rotate it. And we end up with this second molecule. So these are the same molecule. However, what if we had two different substituents? So if we have one methyl group here, and then another methyl group here, and I'll draw the hydrogens in explicitly. And then if we draw, for example, this other compound with still the cyclopropane base, let's keep this left carbon the same, but now let's switch up the orientation of the other two. So we'll have the methyl group going back instead of towards us. Now, these are what we call stereoisomers, because there's no way we can flip or mirror one compound in order to get the other one. We can't just change our perspective. So these are in fact different molecules. And stereoisomers, even though they have the same connectivity, so they both have a cyclopropane ring, one methyl group at this position, and one methyl group at this position. So same connectivity, but different orientation in three-dimensional space. And stereoisomers can have very different physical properties or chemical properties, which we will talk about in future videos. But I do want to mention that what we call, just some more nomenclature, we call this sort of compound a cis compound. So cis meaning same side, because these methyl groups are on the same side of the ring. So they're both coming out towards us. We call that the cis orientation. Whereas this one we call trans. So trans is across or different sides. And that's where we have one methyl group coming out of the plane and the other going into the plane. So we call that the trans orientation. So what I'm getting at is that with cycloalkanes, where you have more than one substituent, if you ever have two or more substituents, you may have some sort of stereochemistry in your compound that you might have to pay attention to depending on what you're looking at. And just to clarify, remember that this is different from constitutional isomerism. So a constitutional isomer is changing the connectivity. So such as if we take our same disubstituted ring, our cyclopropane ring, this would be a constitutional isomer with, for example, this compound. They have the same number of atoms, so they each have, let's draw it in red here, they each have 1, 2, 3, 4, 5 carbon atoms. 1, 2, 3, 4, 5 carbons, and the requisite number of hydrogens, so that would be what, 3, 6, 8, 9, 10 hydrogens. So these would both be C5H10. However, they're connected differently. So one has a 3-membered ring, one has a 4-membered ring. Those would be considered constitutional isomers. And then we also have talked about previously conformational isomers. Which would be something like when we drew our Newman projections. And if you'd like a little bit more review on drawing these sorts of Newman projections with different conformational isomers, then please take a look at my other video. So maybe this could be one conformational isomer, and then if we rotate this a little bit, we might end up with this orientation, where now these are the exact same compound. However, the single bond is rotated a little bit. So we have two different conformations that have very, very similar chemical properties, but they are indeed the same compound. So now that we've got some definitions out of the way, I do want to take a look at another concept that will be very important as we continue studying cyclic compounds now and into the future, which is ring strain. So ring strain is a very important concept that, like I said, we will be looking at often, and not just right now, but throughout the course. So ring strain is strain caused by either deviations. Here, let's group these into two parts. So ring strain is strain that is caused by two things. So one is deviations in bond angle. So all of our alkanes are, remember, sp3 hybridized because we only have single bonds between those carbons. And if you remember from my previous video, the ideal bond angle for an sp3 hybridized atom is about 109.5 degrees. So, for example, if we have cyclopropane, this is a triangle, right? So this angle is going to be 60 degrees, which is much, much less than the ideal angle. Those carbons want to be arranged 109.5 degrees from each other. So this is going to cause significant strain. And this is aptly called bond angle strain. We also have another type of strain called eclipsing, or also called torsional strain. And that's caused by eclipsed hydrogens on the ring. So for example, if we look at cyclopropane again, we can draw maybe a flat sort of perspective. So imagine this ring is in the plane. And then if we draw our hydrogens on each carbon, these are the only places where the hydrogens are going to be able to move. So we have 3 carbons in a plane, and because it's a triangle, it is, by definition, all those 3 carbons are coplanar. So these hydrogens have nowhere else to go. So there's going to be a lot of eclipsing going on. And remember from that other video on conformational isomers and Newman projections, eclipsing is when those electron clouds are overlapping, and that is significantly high in energy. So it's going to be significantly strained. And let's specify in planar rings. So what we can do to measure this ring strain, how do we know that it exists, or how do we know how much ring strain there is? We can actually use the heat of combustion of different compounds to measure it. So heat of combustion, or enthalpy of combustion, we just write COMB to measure the ring strain. And this heat of combustion is complete combustion. So if you remember maybe from general chemistry, complete combustion is where you supply an excess of oxygen and you form only 2 products. So we form carbon dioxide, at least in the case of a hydrocarbon, right? So right now, up to now, we're only dealing with compounds with carbon and hydrogen. Later we'll get into other atoms, but for now, just hydrocarbons. So again, carbon dioxide and water. and that's going to be our reaction that measures the heat of combustion. And if you can imagine, maybe conceptually, that if the heat of combustion is very high, that means that we have a relatively unstable compound. So if we have a super unstable compound, one that is really going to like to just set on fire or explode or something like that, then it's going to give off a lot of energy, a lot of heat, so its heat of combustion will be high, and we can say that that compound is relatively unstable compared to the products. And on the other hand, if the heat of combustion is pretty low, then it might be a pretty stable compound. So if a compound is pretty happy how it is, doesn't really want to react with anything, then it's not really going to give off that much energy when you react it with oxygen. So that compound could be considered pretty stable. So we could also put some numbers to these values, to these sort of concepts. So if we take propane, so this time just our straight chain propane molecule, its heat of combustion is going to be about negative 472 kcals per mole. Whereas cyclopropane, so same number of carbons, but cyclic, this heat of combustion is actually going to be minus 500. So quite a lot more. And in this case, when I'm talking about more or less, or higher or lower heat of combustion, what I mean is more negative. So heat of combustion is usually going to be negative because it's a combustion reaction, and those are exothermic generally. So these heats of combustion are going to be almost always negative. If we do the same thing for 4 carbons, we have butane and cyclobutane. Might get something like negative 630 kcals per mole for the straight chain, and minus 656 kcals per mole for the cyclic compound. Let's do 2 more sets here. So pentane, minus 787, cyclopentane, minus 794. I'm just going to omit kcals per mole from now on. And then we have hexane and cyclohexane. And this will be right around minus 944, and then minus 945. So we can tell that there are large deviations between the propane and cyclopropane, and butane and cyclobutane. So we can say large difference. And then maybe we have a slightly smaller difference here for pentane versus cyclopentane. And then we see that hexane versus cyclohexane, those are basically almost the same value. So small to 0 difference. And that's very important because, like I said, we can use the heat of combustion to determine how much ring strain exists in a certain compound. When there's a big difference between the straight chain analog, for example propane, this 3-membered compound, 3-carbon compound, and the 3-membered ring, cyclopropane, there's such a large difference that we can tell that much ring strain exists. Big difference in delta H of combustion. will usually signify ring strain. And we see that there's significant ring strain in cyclopropane and cyclobutane, so the 3 and 4 membered rings. It is slightly smaller in a 5-membered ring, so cyclopentane. And there's still a little bit of ring strain, but not too much. And then very, very small in a ring of size 6. So that tells us that the 3 and 4 membered rings are going to be much more reactive usually, because they really want to open up. Those molecules are not very content how they are, and for that they will become much more reactive, because they want to release all that ring strain in terms of heat by opening up or reacting somehow. So the other thing I want to talk about is go back to when I mentioned the torsional strain or eclipsing strain, when we have eclipsing hydrogens. One way we can relieve that is, remember we can't change the ring structure at all in a 3-membered ring, because 3 points are always going to lie in a plane. So if you move any one of those points, the compound is still going to be planar. But for 4-membered rings and above, they can undergo a process called ring puckering, which is just what it sounds like. It's where that 4-membered ring or larger can distort a little bit to relieve some of that torsional strain, or also some of the bond angle strain. So the cyclobutane ring, the 4-membered ring, is not actually planar. When we observe it, it looks something like this. So it's puckered a little bit, and what that does is it relieves some of the eclipsing strain from these hydrogens. So they are not as eclipsed as they would be if it were a planar system. And the same sort of thing for cyclopentane. Cyclopentane is not planar. Kind of puckers at the end like this. And as you can see, this also relieves a lot of the possible torsional strain. So we're going to talk about cyclohexane and substituted cyclohexanes in the next video, because those are going to be a big part of what we discuss in organic chemistry. Cyclohexane is very prevalent. But before we do that, I want to end this video by just talking about one pretty simple reaction. So like I said, a lot of these smaller ring sizes will be a lot more reactive because of that ring strain, and they want to release that energy in the form of heat. Therefore, they'll be much more reactive. They'll participate in some reactions that maybe the larger rings won't. So, for example, if we take our smallest ring size, cyclopropane, and we take that and we mix it with some hydrogen gas, and usually it has to be over this catalyst, palladium over carbon, and this sort of reaction we'll encounter many times throughout all these videos. And this palladium on carbon catalyst is something that's very prevalent in organic chemistry and organic synthesis. Usually what it's like is you take a lot of these basically activated charcoal. It's a very porous carbon, just pure carbon in the form of charcoal, and it's mixed with palladium, kind of shavings or powdered palladium. And that palladium is bound to the carbon, and it helps the hydrogenation reaction, which is what this mixing with hydrogen reaction is called, helps that reaction go a lot quicker. So what happens when you treat one of these strained rings with hydrogen gas is it opens up. So those reactions could be very useful if you're looking to relieve some of that ring strain. You can probably imagine what happens with the same sort of system with the four-membered ring. We can open this up as well. And then what if we take maybe so we call these sorts of rings fused systems, where we have two rings that are joined at adjacent carbons, so this carbon and this carbon here. So again, we can do our hydrogen gas and palladium on carbon. And remember, I said that these compounds want to relieve the ring strain. So however they can do that, they will take the easiest pathway. So what's going to happen is we're actually going to form a cyclohexane ring. And so why is that? Remember, the easiest way to relieve this ring strain is going to be to break this bond right here. So if we break that bond, then we have a six-membered ring with very little ring strain, and our reaction is done. So that concludes my discussion on cycloalkanes, our introduction at least. Thank you again for taking a look at Total Organic Chemistry. As always, please be sure to like and subscribe, and check out my Patreon page, which I will link in the description.